What's up, guys? Welcome to Calculus Club. In this video, we will be talking about horizontal asymptotes, okay? So horizontal asymptotes occur as x goes to positive or negative infinity, all right? And we can talk about horizontal asymptotes when we're looking for the limit as x approaches infinity, like you see there, of f of x. Yeah, so let's get into it. All right, so let's take a look at some horizontal asymptotes here. Here you have a graph of 3x squared over x squared plus 1, okay? And you can see as x goes to positive infinity, this function will go to 3. And as x goes to negative infinity, the function will also go towards 3, okay? So we say that the limit as x approaches negative infinity of f of x and the limit as x approaches positive infinity of f of x will both be equal to 3. And you can also see that in the table. So if you had a table here, you can see that as these negative values get bigger and bigger, you will be approaching 3. And as these positive values get bigger and bigger, you will also be approaching 3, okay? And actually, I should say as those negative values get smaller and smaller, right? As the absolute value gets bigger and bigger. All right, so let's talk a little bit horizontal asymptote. The line y equal L is a horizontal asymptote if the limit as x approaches negative or positive infinity of f of x equals to L. Then you will have a horizontal asymptote, okay? Here's a very obvious example. As we go to positive infinity, it's approaching 2. As we go to negative infinity, it's approaching negative 2. Here's another example. Clearly, it's going to 2 as we approach negative infinity. But what about as we approach positive infinity? Well, it doesn't matter that it crosses the graph there at 1 because we're not concerned with what's happening at 1. We're concerned with what's happening as we go to infinity. And as we go to infinity, this function will approach positive 2. All right. One more, kind of an interesting one here, a little bit different. So this also, we say, you can see here the sine x is going to look like this. It's going to oscillate, but as it oscillates, it gets closer and closer and closer to 0. So we actually say the limit as x approaches infinity of sine x over x equals 0. So there is a horizontal asymptote at 0 because it gets closer and closer, all right? The way you'll prove this, and we'll prove this in a second, is using the squeeze theorem. So you should remember the squeeze theorem from just the previous video, okay? But we'll get into it. All right, so the next thing I want to talk about is dividing by infinity, okay? So imagine that you have 5 units of something, okay? And you divide them into an infinite number of parts. Well, each one of those parts is going to get smaller and smaller and smaller, pretty much equaling to 0. Okay, let me give you a quick example. Imagine we have 5 of something, and we divide them into 10 parts. Well, each of those parts would be 0.5. What about if we divided those 5 things into 100 parts? Well, each part would be 0.05. How about 1,000 parts? 0.005, right? And this goes on so forth and so forth, 0.00000000005. And then as you go to infinity, you're going to be adding more and more and more zeros. So pretty much this becomes so small that it equals to 0. So it's kind of like the limit, right? The limit of each part approaches 0. So we say 5 divided by infinity will be 0, okay? And it will also be the case that 5 divided by negative infinity will also be 0. And if that confuses you at all, you could always bring the negative up top. Negative 5 divided by infinity would clearly be 0, right? So you need that information in order to solve this next problem. So I want you to think about these two functions here, all right? Or that one function, these two problems here, okay? What would be the limit as x approaches infinity of each of those? All right, so whenever you're evaluating a limit, the first thing you do is plug in. When I plug in infinity, what do I have? I have 5 minus 3 over infinity, right? Well, as I just said, 3 divided by infinity is 0. So 5 minus 0 is just 5. Okay? Negative infinity, same thing. When I plug in, 5 minus 3 over negative infinity. And like I just said, any number, any constant divided by infinity is going to be 0. Okay, so that will also equal 5. And actually, I didn't mention that in the first. I just said 5 divided by infinity is 0, right? Any constant divided by infinity will be 0, okay? Yeah, so now I want you to think about the limit as x approaches 0 of this, okay? So you've just done these in the previous video. Go ahead and see if you can solve these, and then we'll talk about them. So pause the video and try these. All right, so I hope you paused the video here and you gave these a shot. So first of all, what happens? When I plug in 0, right? 3 divided by 0, a number over 0 will always be a vertical asymptote, okay? So we will have a vertical asymptote here at 0, okay? And let's solve the left and the right. So as x approaches 0 from the right, what I'm going to do is I'm just going to take a number really close to 0 but really small, like 0.000001, right? So that's going to be like 5 minus 3 over 0.0. And actually, I can do however many I want. But what you're going to notice is as I do more and more zeros, as I let this be closer and closer to 0, 3 divided by this is already like 3 million maybe. Minus 3 million, minus 30 million, minus 300 million, right? Minus 3 billion. What's happened here is going to negative infinity. So as I approach 0 from the right, that one is going to be negative infinity. As I approach 0 from the left, now that's just going to be a negative 0.001, which is like a negative 3 million, negative 30 million, right? So on and so forth. But a minus and a negative is going to make that positive. So that's going to be a 5 plus infinity, which is just going to be a positive infinity. All right, so look at this. We have vertical asymptote. We're going to negative infinity, positive infinity. We're going to 5 at both horizontal asymptotes. If we graph this, this is what it looks like. Notice at 0, we have the vertical asymptote. From the left, going to positive infinity, right, negative infinity. And then at 5, here we have a horizontal asymptote. All right, so this is a really good slide because it kind of brings together horizontal asymptote and vertical asymptote. A lot of times students get confused. Limit as x approaches infinity, vertical asymptote, horizontal asymptote, right? This is a great slide to go back to if you're ever having trouble remembering the difference between horizontal asymptote and vertical asymptote. All right, so now let's talk about some trigonometric limits and the squeeze theorem, okay? So I'm going to give you a couple limits here. Pause the video and think about these for a second. All right, so I hope you paused the video. So A, what happens with sine of x? Well, sine of x is always an oscillating function, right? It's going from -1 to +1 to -1 to +1 to -1 to +1. And it does it forever, okay? So because this always oscillates and it's not getting smaller, right? We say that this limit does not exist, okay? The second one, part B, you've already seen. The top oscillates, but because that bottom is becoming bigger and bigger, it's making that oscillation smaller and smaller. So we say that that one equals to 0. But I'm going to show you how to prove that with the squeeze theorem, okay? So, squeeze theorem for this one. First of all, we know sine of x is always between -1 and 1, right? Now what we can do is we can divide everything by x, right? This equality will still hold true if we divide all of these by x. And now we've bounded sine x over x between -1 over x and 1 over x. All right? Now what we're going to do is we're going to take the limit, take a look at the limit of both of these, okay? So go ahead and pause the video, do these. All right, so I hope you realize that both of these will be 0, okay? Now, because the limit as x approaches infinity of -1 over x is 0 and 1 over x is 0, then we know sine x over x must also be 0, okay? So that's how you prove that using the squeeze theorem. And there's a picture to make it a little bit clearer. Okay, so now we're going to talk about rational functions. Okay, so what is a rational function? So a rational function is a ratio of polynomials. All right, how do I remember that? Well, I remember this word rational has ratio in the beginning. So for me, when I see that, I remember ratio. Ratio of what? Ratio of polynomials. Okay, and a polynomial is just like you see here. 2x plus 5 is a polynomial. 3x squared plus 1 is a polynomial. 3x squared plus 2x plus 5 is a polynomial, right? It's just those combinations of coefficient variable raised to degree, okay? And you can Google if you want to be a little more precise on what is a polynomial. So how do we solve a polynomial? If we're going to infinity, what we can do is we can divide by the highest degree in the denominator. All right, so you look here, the denominator is 3x squared plus 1. The highest degree is 2. So what we can do is we can divide everything by x squared. All right, what we're really doing here is we're multiplying top and bottom by 1 over x squared, which is just multiplying by 1, right? You're not going to change anything with the limit. We've been doing this all the time. So then you're going to get 2x over x squared, 5 over x squared, 3x squared over x squared, 1 over x squared, right? Now, these are going to reduce, okay? So when we reduce these x squareds cross out, this x and 1x crosses out, and you're going to be left with this, 2 over x, 5 over x squared, 3, 1 over x squared. Now we plug in infinity, right? 2 over infinity is 0, 5 over infinity is 0, 1 over infinity squared is infinity, which is 0. Okay, sorry, should have mentioned that. And so what are you going to get? You're going to be left with 0 over 3, which is of course just 0. So we say the limit as x approaches infinity of that rational function will be 0. All right, let's do another one. So go ahead and follow. I want you to pause the video and try this. Follow the same rule, divide by the highest degree in the denominator and see what happens. All right, so I hope you did that. I hope you tried it. Once you divide by the highest degree, you're going to be left with 2 over 3, 5 over x squared, 1 over x squared. Both of these will go to 0, and you'll be left simply with 2 over 3 as that limit. Okay? The next one, same thing. Pause the video and try this. All right, so I hope you pause the video, divide everything by x squared, and you're going to be left with 2x. Plus 5 over x squared, 3 plus 1 over x squared. As we go to infinity, this will go to 0, this will go to 0, but this, 2 times infinity is infinity. So this is going to be infinity. You're going to be left with infinity over 3, which is still infinity. Okay, and infinity divided by any constant will always be infinity. Even in infinity divided by a billion will still be infinity. Okay. So yeah, so now I've shown you 3 different rational functions, okay? Now there's a little bit of a pattern here, all right? And so what you can do, there's a bit of a shortcut. So anytime the degree of the denominator, okay, is less than, okay, so the degree of the numerator is less than the degree of the denominator, like here. This is a 1, this is a 2. This will always be 0. The limit as it goes to positive or negative infinity will always be 0. Okay? When they are equal, like they are here, 2 and 2, right? Then you look at the lead coefficients. Okay? So the lead coefficients mean the coefficient in front of the highest degree. So here you have a 2 and a 3. So this will be 2 over 3. Okay? In the last situation, you have the top bigger than the bottom. If the top's greater than the bottom, it will always be infinity, okay? So whenever you have a rational function, you can, 1, divide by the biggest degree in the denominator, which is the safe way to do it, or you can remember these rules, which also is, is safe if you remember them correctly, right? This is always true. So just a couple more facts about horizontal asymptotes and I'll wrap up the video. I'm getting super hot. Jeez, I'm sweating here. My AC's broken. All right, horizontal asymptote So a function can have at most two horizontal asymptotes, one to the right and one to the left, okay? When we have a horizontal asymptote at y equal L, we say the limit as x approaches positive or negative infinity exists, and it is equal to that L, all right? And the last thing I already talked about, any constant divided by positive or negative infinity will always be 0. All right? So yeah, so that wraps up horizontal asymptotes. So I hope you enjoyed the video and it helps you in your calculus class. If you could support me, give me a like, comment, subscribe. Those things really help me a lot to reach more students. So hope you tune in for the next one and have a great day. Bye-bye.